Good morning, everyone. I'm here to present investigation portability in Chapel for tree-based search, optimization GPU-powered cluster. My name is Tiago Carneiro. I'm a researcher at IMEC Leuven. All the authors are Engin Kairakli Aglu from HPE, Guillaume Erbeck, University of Luxembourg, and Professor Melab, University of Leeds. As my time is short, let's go straight to the point. We have an application called Chapel-based optimization. It's a distributed tree-based search for solving combinatorial optimization problems. Depending on the problem, it's backtracking or it's a branch and bound, okay? The distribution version of it has the distributed program features on top of the distributed iterators module. So we don't have to implement the load balancing, work distribution, metric reduction, termination criteria, which is handy because this saves something like 2,000 lines for us, and we don't lose a lot of performance. The problem is when we go to the infranode aspects of our search, now we have to mix Chapel plus CUDA or Chapel plus heap for AMD computer AMD's GPUs. And when we have a look at our infranode code, it's very redundant and difficult to maintain because the application begins with Chapel, goes to the interoperability layer that can call CUDA and the C code that calls the kernel, if it's an NVIDIA system, or a heap code otherwise, then goes to Chapel again. As I said, this is very redundant, difficult to maintain. We would like to replace this with Chapel native GPU support, okay? That's the objective. So we would like to see whether or not we could have code portability and performance portability in distributed executive optimization, the case of this application, and whether or not it's worth in terms of programming effort, because maybe the code gets much bigger than this interoperability code. So to answer those two questions, let's say, we have to implement several, let's say, parallel backtrackings for solve the NQueen's problem. Three single node ones, multi-GPUs, one in heap plus OpenP, one in CUDA plus OpenP, that's the baseline for the speed up. A Chapel only version of the baseline. The distributed one that I showed you, which has Chapel plus CUDA or Chapel plus heap for the intranode aspects of the code. And one distributed application, multi-GPU distributed, that only uses Chapel native GPU support, okay? We know that the NQueen is not a real problem, more a toy problem, but we use the NQueens as a proof of concept. If this backtracking, what we are expecting, we can see in this backtrack implementation, we go to a branch and bound for solving combinatorial optimization problems, okay? The size of the queens are size 18 to 22. It's really big. And the computers we use it too. The permuter top 12 of top 500, 228 computer nodes, up to 512 GPUs, 4 GPUs per node. One AMD system, the top one, Frontier, 228 computer nodes as well, but 8 to 125, 1024 GPUs. The problem is that on this computer, our jobs could only take 2 hours. So some points of my graphs, they are missing, and some points I had to guess the execution time of the baseline, so I could get a full line, okay? But I'm going to tell you when those guesses are used. The first results are the execution time, distributed execution time. On my left here, the CUDA, what we can see is that for the smallest loads, Chapel and CUDA, they are more or less equivalent. Then the performance, the performance gap increases a bit. Then it starts to be flat. Chapel is 7% slower than CUDA plus Chapel. Okay, but the slowest one is 30% slower. But the one that's important for us, the big loads, because we want to solve big problems, Chapel is around 7% slower. When it comes to the AMD system, something very, let's say, curious happens. For the smallest loads, Chapel is almost 4 times lower than heap. Then this performance gap goes down, and Chapel performs a bit faster. But why? This needs more investigation. We went to the intranode or the single node execution. we could see that in CUDA, what we saw in distributed compute, we can see on a single node. Chapel, the performance gap is not that big. Chapel versus CUDA increase a little bit and get stable. For AMD is the same. I didn't put here the smaller loads, but it's very big, the gap. Then goes down, and then Chapel starts to be a bit faster, starts to perform a bit faster than the heap. This we need more investigation, okay, to understand this, to maybe see the PTX code if something is generated that's causing this a kind of overhead for the smaller loads. But this I think needs more investigation, but give some clues about what's happening on the distributed executions. In terms of speed up, what we can see here that something that for me the application scales well on 128 computer for the biggest loads. When there is load enough for 512 GPUs, the hybrid CUDA plus Chapel achieves 60% of the strong scaling efficiency. In Chapel, 55%. I think it's okay. This also means that the distributed iterator module, when it's well tuned, works even in higher scales. And we didn't have to implement these communication aspects of the search. We rely on the distributed iterator. So, okay, that's, I think, a good result for the application itself and for the distributed iterators in Chapel. Those points here I had to guess, okay? I had to guess the value of one computer node solving the queens of size 22 based on the kind of heuristic that the next queen is 10 times slower, no, not 10 times slower, the execution of one queen of size n plus 1 is 10 times longer than the queens of size n. Making this guess, I could have the full line for Chapel and 1 point for heap because the budget, we could not run a lot of experiments that took more than 2 hours, okay? We could see that similar results, hybrid heap, 61% of strong scale efficiency. Chapel, 55% of strong scale efficiency, a bit better than CUDA here, that was 55. So similar results on two different architecture when we didn't change the code for this. And just conclusions, we could say that it's possible to use Chapel to program all levels of parallelism of a large-scale cluster in the context of our application, of course. Both on both systems, our Chapel-based application could reach similar strong scale efficiency compared to its hybrid counterpart, okay? And also using Chapel native GPU support makes by using Chapel native GPU support, replacing all that interoperability code makes the full application 65% shorter, much shorter. But this is the case where we can keep only one application, only Chapel. And when we solve that problem of, not the problem, when we understand that issue of the heap code, why for the smaller load it's smaller, and when we have more points, maybe we can say that's possible to achieve both code performance and portability in distributed executive optimization using Chapel native GPU support. And those results are from a paper that we are going to present in Europar 2024. Okay, it's just a piece of the presentation that we are going to present. And that's my presentation, guys. Thank you.
Thanks, Tiago.